Welcome circuit students. In this demo video we're going to discuss ways to use our oscilloscope and function generator and the concept of resonance to identify the inductance in some maybe unconventional inductors. So one problem that you might run across in your work in electronics is you may not always have the exact size of a particular passive component you might need. As we know, capacitors come in a huge variety of sizes, ranging from picofarads all the way up to farads, usually the higher values being polarized capacitors. Inductors that would be appropriate to fit on a proto board, though, typically max out in the 0.1 Henry and below. Of course, we can find others, but you may or may not have them in your kit. Furthermore, as we found, inductor markings are not necessarily as consistent as resistor markings or maybe even capacitor markings. So you might end up with something that could function as an inductor, but you may be uncertain of how to use it because you can't design around its inductance because you might not know what it is. If you recall, our concept of resonance is a very powerful concept from the point of view of relating frequency of an applied signal to the value of both an inductor and a capacitor that are either in series or parallel. Well, one nice thing that we can use is solve for one of the three variables while controlling the other two. So if we have a variety of capacitors for which we know the value, and we can use our function generator, or if you're using a Picoscope, your arbitrary waveform generator, we can set the frequency or scan across several frequencies, know the value of our capacitor, and when we identify a point that corresponds to resonance, we then have F resonance, and we can go back through our resonance expression and basically use basic algebra to solve for the value of inductance. Now, you might wonder, why do I have two transformers and a switch here? The reason that I'm using these for today's demo is that, as you probably know, a transformer is nothing other than one or more inductors, either placed concentric in the case of an auto transformer or isolated electrically and connected with a magnetic field in the case of an isolation transformer. And as you can see, these come in all different shapes and sizes. So this larger one is a typical step-down transformer that's designed to take our nominal 110 volt wall power, or grid power, AC grid power, and step it down to somewhere around 12 volts, which is typical for use in DC power applications. So that 12 volts would probably then be applied to a diode rectifier bridge with some smoothing capacitors, and this might be the foundation of a power supply. It will handle 300 milliamps. So that's based on the ampacity of the windings, and its voltage rating at the 110 volts is going to be determined by whatever insulation and proximity is used on our primary windings. So when we talk about windings on a transformer, each winding is nothing more than an inductor, and depending on the diameter of the coil, the length of the coil, the number of wraps, that will determine its inductance. So we don't know what those are, but we can use resonance with a known capacitor value and a sweep of applied frequencies to effectively measure inductance. So we have two inductors in this transformer. We have the inductor, which basically is created by the primary winding, which we're told PR 110 volts red leads. We have a nice label that says these are the leads that will lead us to our primary winding, and then effectively we have our choice of two different inductors in the form of the secondary. It probably has a different number of loops. N is different than the primary, and it may have a different diameter, and very likely has a different gauge of wire. It needs to be designed to handle higher current. And because it has a center tap, that's what the CT means in our labeling. We can either use On the secondary side, we have easy access to all the windings or half of them in either case. So as we go on in this video, we're going to measure the actual inductance L of the primary side of this, which we would expect to probably be fairly large. Okay, so here's our scaled down version of another transformer. This is an audio transformer. We went ahead in an earlier video, which you may or may not have seen in your course. This was used as an example of measuring step up, step down ratios in a transformer. But we can also use either the primary or secondary side of this, which is actually an isolation transformer. So I have two inductors in it. I can use either one as a standalone inductor. And in fact, these are, if you were to look at the data sheet for this, there's 6 pins. Each of these 3 sets of pins on either side corresponds to its own standalone inductor winding and their center tap. So basically I have a primary side, which is labeled with a P. I don't know if you can see, it's lit up. It's labeled with a P right here. And so that has a different number of wraps, possible different length and diameter than the other side. So I have a variety of actual inductances that I can get from this. And last but not least is a switch. This is a relay. And if you were to look up this number and find a data sheet, you would find that on the back side you have some leads. These are not showing up so well in the camera. You have 8 leads, and 3 are spaced more closely. Leads 1, and I believe it's labeled 16 over here. Actually, have a coil. They have an inductor between them, and that's providing magnetization for a switching mechanism. So this is a relay, and so part of that relay mechanism is a standalone inductor. And so if we were shy of an inductor and this happened to have the inductance that we needed for another circuit, we could use this as a standalone inductor if we needed to. Not necessarily advocating using relay components or transformers as standalone inductors. If you're going to build a permanent circuit, you'd be best off buying an appropriate standalone passive component that really fits your needs. But one of the points of this exercise is to remind ourselves that multiple different components rely on the same principle. And the principle of inductance is fundamental to relays and switches, transformers, as well as standalone inductors that work together with resistors, capacitors, and maybe active components in a circuit. So having seen all of our unconventional inductors, I'm going to do a last bit of filming with my camera and show my protoboard. I have a capacitor and a resistor, and then I'm going to bring in a signal on my power rail, and I have a measurement point that I've made that is basically between what will be a series of the various unconventional inductors and a capacitor. I'll use a different value for the different inductors versus this resistor. So I'm going to create a series resonant circuit with the unknown inductor and a capacitor, and then I'm going to compare the voltage signal as I scan frequency over the whole circuit to the voltage drop over my resistor. And I'm going to use that to help me identify the resonance frequencies. And for that, I'm going to use 2 functions on my oscilloscope spectrum analyzer, both the scope and the spectrum analyzer. I'm going to start with the spectrum analyzer and sweep across different frequencies. And I'm going to use that to dial in a rough estimate of where I'm going to find resonance. Then I'm going to switch back to my scope, and I'm going to look for the place where the voltage signal for the whole circuit and the voltage signal for the voltage drop over my resistor are in phase, because we know that in a series resonant circuit at resonance, all of my inductive and capacitive reactance cancels out, and so there's no phase difference between the whole circuit. The whole circuit becomes purely resistive, so there's no phase difference between the whole circuit and the voltage drop over the resistor. So that will help me confirm the exact frequency of resonance. Then I use F resonance related to value for my known value for my capacitor, and I can back out the value of the portion of each of these inductive devices that I'm using as an inductor. So I'm going to end this recording and turn off the camera and then see you back with a Picoscope, and I'll have one or another inductor hooked up in series in a series resonant circuit, and we'll start making the measurements and identifying the inductance of these three different two transformers and a switching device. Welcome AC circuit students. In this part of our demo video we are using our Picoscope, USB oscilloscope, and function generator and frequency analyzer to identify the inductance of the inductor portion of a switch that we showed in our previous video. For this series we're using the concept of resonance to identify the inductance of portions of switches or relays and transformers that could be used as inductors, and basically emphasizing the concept of the inductive theory of operation of all of these devices, and also showing a good handy trick for measuring components that may be difficult to identify. So I have already built on my proto board a series resonant circuit. I have the inductor portion of my Hila-Shun HLS 4078 12 volt small proto board compatible relay, which I showed in the earlier video, and I'm going to apply a variable frequency signal across the inductor portion of that relay and a 47 nanofarad capacitor, and I'm going to simultaneously measure the voltage signal magnitude over the whole circuit and over a resistor which I've placed in series with that series resonant couple. So what you're seeing right now is my Picoscope screen. Nothing's moving because my two data collection channels are turned off. Excuse me, I'm running the scope, so if I turned them on I would see something. I'm going to go ahead and move over to my my spectrum analyzer or frequency based analyzer. We're having to wait a little bit for the Picoscope to warm up. I think it says it's waiting for data, so it's not going to show anything until I turn either of these two channels on. And I am running and ready to collect data. So the first thing I'm going to do is I'm going to set up my what's called FFT options. This means fast Fourier transform. This is the mode by which the Picoscope collects frequency-based data. And this will help us display the data in a way that it's easy to see the resonance signals. We want to see a peak basically on the signal over our resistor, and we want to see a trough over the whole circuit, because with series resonance, of course, as we approach the resonant frequency, we're going to decrease the overall impedance of the inductor and the capacitor, and theoretically, in an ideal scenario, right at resonance there will be no inductive or capacitive net reactance. They'll totally cancel each other out, and all we'll be left with is a purely resistive circuit. So the total impedance will be at a minimum over the whole circuit, but the actual impedance across the resistor as a fraction of the whole circuit will be at a maximum. And so we should see a kind of a trough on the whole circuit and a peak for the impedance over the voltage drop due to the impedance of the resistor, because we're just measuring voltage drops with our instrument, our Picoscope. So a good way to display this, and I've done a little pathfinder here, and you can go ahead and experiment with your number of frequencies that you display in a group, the spectrum bins. I found that using 512 for the frequency range that I'm going to use gives me a good signal and makes it easy to display resonance. And the Blackman-Harris window where we look at a window of frequencies and how we average the signal within that window. That's great for just about any application, and you'll find that that's discussed a little bit in your Picoscope manual if you want to take a look. We'll need to do a peak hold. So what we're going to do is we're going to measure the voltage signal magnitude over a range of frequencies in a window. We're going to use 512 little windows over whatever frequency range we want to display. We're going to use the Blackman-Harris model to display the maximum, and then we're only going to display the top number. And we're going to use a linear scale because we don't have a really high Q factor in the circuit. So if we displayed on the log scale, we would compress it. Typically you would need a log scale for resonance, especially for radio frequency or for something with a high Q factor, but we're not going to get a lot of decibels of change. So it's going to be easier for us to see this with a linear scale. So these are our data collection parameters that just make it easier for us to see. Now, the choice then becomes, where do we think resonance is? You know, how big of an inductor do we think this is? Because for a given capacitance, the bigger the inductor, the lower the frequency we would expect resonance. We can go back to our algebraic expression for F resonance. So I'm going to cheat a little bit since I've already experimented with this and determined it. I have found that a frequency sweep somewhere over, we'll go very, very low. And again, this is a bit of an iterative procedure. If you were to determine this from scratch, you would start with a very wide window and then narrow it down to better find the resonant frequency. But I'm going to scan from 5 Hertz, very low, and I'm going to go up to, let's say 3 Hertz. No, let's go to 2. Obviously, I'm cheating a little bit. It's 2 Hertz. And I'm going to turn my signal on, which allows me to change my frequency increment. It won't move if you don't turn the signal on. So I'm going to move the frequency in as small an increment as I can, which will give me a better resolution as I scan through. Now, I want my X scale of frequencies to more or less correspond to my stop frequency. So, oops, it won't change here. So I'm gonna, it kind of wants this to be on. So now it gives me my range of frequency. So I'm going to put an X scale of 2 kilohertz. So I already know resonance is somewhere in here, but I don't know where. So I'm going to sweep to find it. And I'm leaving my my voltage collection signals on auto because I don't quite know how they are. Eventually I might want to, if I wanted to show a very pretty plot of resonance, I might want to collect for a while and then put them on a hold over a Y scale that showed what I wanted. But I'm just basically looking to see where will I see a trough on my full circuit voltage and a peak on my resistor voltage. So I'm running. And now I'm going to go ahead and start sweeping my signal. And the first thing I'm going to check is to make sure I'm on peak hold. So as you can see, it looks like I'm collecting a bunch of peaks, and rather than having a line go across my display, you can see that what I'm actually collecting is 100 millihertz window. And I'm collecting a voltage signal over that window, averaging it according to the Blackman-Harris model, and then displaying the top. So you can see we're only displaying the top number, and we are sweeping up. We can do sweep up and down. So now you can see it's changing. My cursor is showing how it's changing as we go across the screen. So I'm collecting data and I'm displaying the latest data each time. And what we're doing effectively is we're getting a better and better signal. So every time we sweep, and we're sweeping up and down in frequency, we're getting a little bit better idea of what we're doing each time. And we should start to see a clearer and clearer signal as we go along and we wait. So we might want to Might want to have a coffee or something as we wait, but we can already begin to see our red signal is channel B, and that's looking at the voltage drop over my resistor. So we can already see the beginnings of what looks like a peak here somewhere between 700 hertz and 1000 hertz. Definitely at very low frequencies, I have almost no voltage drop over my resistor. Well, that's because it's all dropping over the capacitor, which is acting like an open as I'm down here at my practically DC frequencies. And then as I go to higher frequencies, I again see the voltage drop over the resistor decreasing, but not as fast. So you can see that the inductor is not responding as quickly to frequency as the capacitor, so that might tell us something about its relative value. And it's a little bit harder to see the trough, but we can basically, it's much easier to see the peak in the resistor, but we can also see a corresponding decrease. If we look at the tops of the blue signal and we kind of draw a line, imaginary line across the top, we can see that it decreases from something around 700 millivolts over at the DC side down to maybe 600, right underneath where that peak for the voltage signal over the resistor is, and then it goes back up to 650 as we get out to higher frequencies where the inductor would be limiting current and therefore limiting voltage drop over the resistor. The reason we see a trough with the whole circuit voltage, part of that has to do with the sag of the Picoscope. So as we get to resonance, the overall impedance of our circuit decreases, and the Picoscope can't supply the current, so the voltage actually sags. So as we hit that low resistance or low impedance, in this case frequency, we're actually relying on the non-stiff nature of our source to help us identify where resonance is. Well, at this point we can probably stop. So I stopped the signal sweep, and we ended at a point where, for whatever reason, we're not on a scale. We're at a 50 millivolt scale for the whole circuit, so we can't see that. But we'll go ahead and use our frequency, or our x-axis ruler, and we'll pick a frequency somewhere where we think the top of this peak is. It's kind of a long shot call here, because it could be anywhere from maybe 1100 hertz, 1.1 kilohertz. Maybe it's 800. It's definitely not less than 800. So it's somewhere between probably 800 and 1000. It seems reasonable based on where this peak would be that we're seeing. So to dial it in a little bit differently, we're going to use phase difference, and for that we need to go back to our oscilloscope. So we're going to go up to our push buttons and click the leftmost one and go back to time-based signals. So now we've got our scope displayed. So we're not going to sweep the frequency now. Now we're going to use our AWG, and we're going to, of course, put it back to sine wave. And we're going to say, all right, let's start with the lowest frequency that we identified with our spectrum analyzer. So we'll go to 800 hertz. And we'll turn it on. And we'll turn on our... Now we definitely need both channels. So we're going to simultaneously display the voltage signal that corresponds to the whole circuit in blue and voltage drop over the resistor in red. We're going to enable a trigger. So we tell the oscilloscope where to stop drawing new signals, and we're going to increase our time base so we can visualize our signal. So we can easily see the phase difference between our signals. So basically, if we were to take a spot here where our trigger is, our whole circuit is crossing the y equals 0 axis here on the blue, so it's heading up, and you can see our red signal kind of did that at an earlier time. So basically the the voltage drop over the resistor is leading that of the whole circuit. We want to find the frequency for which neither one is lagging or leading. We want them right on top of each other because that corresponds to resonance. So knowing that that our peak was in our frequency display was somewhere between 800 and 1000, we're gonna just use our buttons to increase frequency and see if we get any closer. Oh, yeah. So I went to 900 and we can see how we got much closer to the two being superimposed. And I'm going to keep adjusting my time basis so I can really see that difference. And so I'm going to start nudging it up in increments of 10. So there's 910. Didn't really change a lot, maybe a little. 920. Oh, I'm not changing it here. 20. So you can see the red curve and the blue. If you look right here near where the trigger is, you can see them pulling together. We want to find the frequency where they both cross that 0 point at the same time. And time meaning the same X point. So you can see they're almost on top of each other. Try 940. Oh, okay, so 940 could be it. Does 950 look any better? Maybe. So now we'll see if we go higher at this point, what we should get is a point where the blue curve starts to lead the red. So let's put in something like 990 to confirm. Yes, so now the red curve is ahead, which means it takes more time for it to get to the same place, so it's now lagging. So the point where they were superimposed is right around 950 hertz. So that is F resonance, 950 hertz. So if we use our formula for resonance, which says F resonance is 1 over 2 pi times the square root of LC. So 2 pi times square root of LC is all together in the denominator, equaling F resonance. We can put in 950 for F resonance. We can put in 47 times 10 to the minus 9 for our C, and then solve for L. So it's just algebra. And if we do that, we end up getting about 0.6 henries for the inductance value. So that's 6/10 of a henry. So that is a reasonably large inductor as protoboard type inductors go. And in fact, in my kit, my largest value of inductor is 100 millihenries. So I now have the option of something 6 times that size if I were to need it. So I'm going to go ahead and use the same principle to measure the inductance of the primary of the small audio transformer. So what I'm doing is I'm going to add it to my protoboard. And again, I'm going to do a little bit of cheating because I already know I've already done the Pathfinder kind of experimenting with frequencies. So I'm positioning it on my protoboard, and I already know that a different capacitor allows me to visualize resonance differently on this. So I'm going to go ahead and put the primary coil of that little audio transformer in series with a 4.7 nanofarad. So I'm stepping my capacitance down by a factor of 10. And that actually is going to give me a little bit clearer view of resonance there. But otherwise, same thing. The primary coil of my audio transformer is now in series with a 4.7 nanofarad capacitor. I'm using the same resistor, and they're all together in series. So I'm going to go back to my spectrum analyzer. I'm going to click on magnitude to kind of clear it. Go back to peak hold, and it turns out this 512 bins spectral resolution in the Blackman-Harris data collection scheme works really well to show resonance for just about everything that we're going to look at today. So we're going to keep that the same. And I am going to sweep, in this case, from I'm going to go again from 5 hertz, and I'm going to go up to 12 kilohertz. And let's go to 10. And have to make sure that I actually get what I thought I did. Okay, so I'm using the smallest frequency increment to change 100 millihertz. I'm going to go start frequency of 5. I'm going to sweep to 10 kilohertz. I am running, and I have both of my channels turned on. So let's see what I get. I should start collecting. So here we go. We're collecting very small peaks here. Oops. I'm not going to be able to display this very well because I'm only visualizing 2 kilohertz on the x-axis. I want to see all 10. So I better go change this. I'm going to go to a 12 kilohertz full scale X display. So I scaled up my X display. This is like going to a different time basis on your scope. So let's try that again. So because we've gone to a larger frequency X scale, all of those small window peaks that we were plotting when we were only displaying full scale of 2, now they're all stuck together. And we're only taking the very high points. So this line is actually the peaks of a whole bunch of those little Gaussian displays that we saw when we were only had a full scale of 2 kilohertz. That's pretty typical as we're collecting in frequency mode. So again, we are looking at kilohertz on the bottom. So we go from 0, 2 kilohertz, 4 kilohertz, 6, and we can see our red display is voltage drop over our series resistor, and it's got a peak somewhere between, say, 3 and maybe 5 or 6, and we can clearly see the corresponding trough in our full circuit voltage. So we know that resonance it's somewhere between here and who knows. We'll call it it's at no lower a frequency than maybe 3, and we think it's going to be less than 5. And the noise that we just saw was literally me bumping my proto board and grabbing the sliders. So I can stop this, and I know where to start looking on when I do my scope display, where I'm going to look for the lack of a phase shift between my full circuit voltage drop and my resistor voltage drop. So I'm not applying a signal anymore, and I'm going to switch over to my scope mode. So again, 3 kilohertz to 5 kilohertz. We think we're going to find resonance somewhere in there. So this ends up being a bit of a resonance hunt. So let's start with 3. So 3000, and we're going to turn it on. We're running. Why are we not seeing anything? We didn't turn our channels on. Let's ask our oscilloscope to look for something. Let's give it a trigger so that it stops. Okay, we're definitely not at resonance of 3 kilohertz because we've got a very clear phase shift. So again, our resistor is leading our full circuit. So let's use our index arrows on our AWG to just start increasing frequency. So 4, they got much closer. I'm going to decrease the time base so we can keep spreading that out. And at 5, we overshot a bit. So let's go. Now we'll start kind of creeping up on it again. Let's look at 4,500. Almost right on the money. So in fact, we can spread it out a little bit more and look. That is almost perfect overlap. We can see that both curves cross the x-axis at exactly the same time point, which happens to be underneath our trigger diamond. So we know that we have an F resonance of 4.5. and we can put that together with our 4.7 nanofarad capacitor, back ourselves through our F resonance formula, and get an inductance of about 1/4 of a Henry, between 0.2 and 0.25. My earlier measurement, I actually calculated or measured about 5,000 hertz for F resonance, and that would have given me an inductance of 0.2156 Henrys, 0.22 Henrys. I wouldn't give myself more than 2 decimal places given the uncertainty of this measurement. Why am I getting a different value today? Hard to tell. Some of it could just be difference in the way I have the circuit hooked up. I could have some inadvertent additional capacitance or inductance. You can see depending on exactly how you call this point, I may have overshot and now be lagging with the resistor versus full circuit. So, but it's close. It's between 0.2 and 1/4 of a Henry. So I at least have it within about an order of magnitude. So now I have around 0.6 of a Henry inductor, and I have 1/4 of a Henry inductor. I could do the same thing for the secondary on this transformer, and there's it's very, very likely that I would get a lower value for that inductance, simply because we know that for a transformer secondary, if it's a step down transformer, that it would have a lower number of loops, and that would give me a lower inductance. I don't know, I would have to refer to my step up, step down ratio for this transformer to get an idea, or I could just flip it around and repeat these measurements. But I will move on to my wall power step down transformer, my 110 volt to 12 volt transformer. And for that one I'm going to go back up to my larger capacitor. There is no hard and fast rule for why you would use one capacitor or another. I just found that by moving the capacitor value, I was able to shift the F resonance such that I was able to display it more clearly with my spectrum analyzer and show it a little bit easier with my scope. Obviously, I can change F resonance or FC for the same value of inductance. I'm hooking up my circuit as we speak, so I'm going to double check. I'm collecting signal while I do that. That's why you're seeing noise. So I now have my primary from my 300 milliamp capability larger transformer in series with a 47 nanofarad capacitor, and in series with my kind of indicator resistor. So back I go to my spectrum analyzer. I'm going to clear the display. And for this one, I'm going to want to sweep not too much. So we're going to be down at that a little bit less clear display. So we're gonna scale over. We're gonna use 2 kilohertz full scale on the x-axis, and we're gonna sweep that full amount. So we're gonna sweep from 5 hertz, almost DC, up to 2 kilohertz. We're gonna use the smallest increment we can. We're collecting signal. We're gonna want to use peak hold, and away we go sweeping. And again, you can see we're collecting the midpoint of a given frequency window. We're moving 100 millihertz. Each time the instrument goes to another frequency, it moves over 100 millihertz, and we're collecting 512 bins of frequency as we go along. We're going up and down. So if this is real over here, we could tell ourselves that chances are we're going to have a resonance over here somewhere around, we'll call it maybe 375 hertz, and the instrument is auto scaling as it sweeps through. Each time it fills the whole screen, it actually gives a click. And if you look up here at your scales, you can see that it's changing scale for both of our channels, our full circuit voltage and our resistor voltage. And we're getting something that looks clearer and clearer, like a peak and a trough. The peak is clearer than the trough, so we'll use that. We could probably stop right now and use the 350 kilohertz as our target. See, there's our scale change, and it swept through. So we'll stop the sweep. So we know we have resonance somewhere around 350. So we're going to not waste time. We're going to go right over to our oscilloscope, and we're going to, let's try 350. First guess. We're going to apply that signal. We're going to increase our scale. Nope, almost, but not quite. Our resistor voltage drop is still leading our full circuit a little bit, but not much. So let's creep up on it in increments of 5 hertz. Close, 355. 360. Almost there. 370. Nope, overshot. So now our resistor's lagging. So let's try 365. Very close. Let's spread out our time basis to get a better look. We can see it's still lagging a little bit. So it could have been 360 was right about it. Nope. So it's kind of sensitive because I've spread the scale out quite a bit. Okay, so right around 362, 363. So the exact crossing is now, it's superimposed with a 363 hertz. So that's very low frequency. We can compare that we had F resonance with the same value of capacitor at 950 hertz with our relay inductor. Now with that same capacitor, F resonance is at about a third. So obviously that means we're going to have a corresponding difference in inductance. So if I use 363 as F resonance and I use my capacitance of 47 nanofarads, use my expression for resonance, I end up getting around 4.1 to 4.2 henries for my inductance corresponding to this this primary side of the transformer. That's huge. That's over an order of magnitude larger than my largest standalone inductor that I had in my kit. So by going through this exercise, I effectively gave myself a large number of larger inductors. Now, in addition to my 100 millihenry inductor or 0.1 Henry inductor that I had, I now have a nominal 0.2, a 0.6, and a 4. So I can now build circuits that would require much higher levels of inductance. Caveat to that, by using these, I'll call them unconventional inductors, I don't have any kind of accuracy guarantee. So because these inductors were intended to be used for just simply providing, in one case, mechanical switching, in another case, voltage step up and step down, I don't know what the range is. I don't know how the inductance would necessarily change with frequency. You could see, in fact, on our frequency scans that the high frequency side was much broader than the low frequency. There could very well be a significant amount of resistance, and in fact, in the case of the audio transformer, I actually measured a reasonably high resistance. I think it was something around 70 ohms. So that's a very imperfect inductor. So if I were designing a circuit where I needed of a particular value of inductance, or I needed to know that my inductor had a particular value plus or minus whatever, plus or minus 5 or 10%, this wouldn't probably be the best way to go. There could be a huge, broad range of values that could vary with current, could vary with frequency. Nonetheless, if I needed something that was order of magnitude range, where I could maybe tolerate that broad range in actual inductor value, these might work just fine. Definitely they would work well if I needed to perform some kind of corner of the box experiment where I needed to swing inductance to maybe the highest I would ever expect in a working circuit. This is a great way to do it. Certainly a good alternative to not being able to run a test at all. So that is it for this demo video. Hopefully you've enjoyed deployment of the concept of resonance and a picoscope to identifying some component values using two different principles. And feel free to try that. Also, if you have a known value of an inductor and need to test a capacitor, the same principle would work. So if you can't read the teeny tiny markings on a particular capacitor, this may be an easier way of identifying it than hunting for a magnifier. So happy measurements.